Okay, we're back on air.
Sure.
I guess we are.
Test.
Cool. So let's
Test.
Yep.
Yes.
Okay, perfect. So
apologies again for the technical difficulties. Failed hard drive leads to new OBS setup, all that stuff. So hopefully we are good now and we can edit me out at the end.
Great. So due to our supreme editing skills, this will basically be a seamless transition. Now that Ricky has shown you how we deploy how we provision the infrastructure that stuff actually runs on, let's take a look at the demo application that we're layering on top of the infrastructure. And this is our manufacturing lightweight accelerator, the Manuela demo application. Let me take you quickly through what we're trying to achieve here. We want to do declarative configuration management from the core data center up to the edge, and we're using a distributed GitOps approach to that. So all the configuration is going to be stored in Git and manipulated in Git and applied at the edge. We want to build and test intelligent cloud native apps. So we basically want to do the stuff that we are used to do in the cloud, in the corporate data center, all the way to the edge. We want to do continuous integration, continuous delivery pipelines. We want to do it both for application and for machine learning models. We want to capture the data and for traceability and analytics at the edge and transport it to the central data center so that data scientists can run their training algorithms on the data, but also developers can use it for support purposes. If they want to understand what's actually happening in the field, they can look at the data as well. And want to enable the data scientists to actually train machine learning models and basically deploy them again from the core down to the edge where they then actually run and do inference. So what is this application that we're looking at? We have 3 different environments that sort of form the deployment backdrop where our application runs. We have the line data server that is close to the production line. We have the factory data center. This is basically a sort of IT environment in the factory itself. And we have a central data center that is sort of the corporate headquarters, let's call it that. And between each one of them, we can assume firewalls to be in place. So there's no way for the central data center to just send a command to the line data server to execute something. So, but this usually the firewalls can be traversed from the line data center to the factory data center and from the factory data center out to the world. Why is that the case? The production equipment that is there is usually quite, I would not say old. That means it's no longer working correctly. That's exactly the point, right? It has a very long lifetime, very long depreciation cycles, and therefore also the IT infrastructure that comes with the production equipment is usually a tad bit older than what we're used to in a data center. So it's very common to find old Windows 90 something servers actually running here and chugging along and just doing what they're designed to do because they work with the production equipment that is out there, with the presses that have a lifetime of 30 or even more years. So of course, these are firewalled off from the rest of the world in order to protect them. Now, if you want to install an application across all of them, that becomes an interesting challenge. So what does our application actually look like? We have the actual sensors and actuators down here that are connected with the field bus to the line data servers. And in our case, because we don't have a hardware rig that we can install everywhere every time we want to show a demo, we're just using this piece of software that simulates sensor data that is being acquired here on the devices through these field buses. These talk MQTT to a broker which is running in the factory data center. That's our AMQ broker that provides an MQTT endpoint that gathers data from the various different sensors and sends that data off to different paths. One of them is our consumer component, which sort of does 2 things. First of all, it feeds a dashboard that sort of visualizes that data to a plant operator, for example. The second thing is it invokes an anomaly detection service. based on Selden Core that is able to sort of see a sequence of measurements in context and identify whether the readings are actually normal or abnormal. And in the case of abnormal measurements, right, there's an alert being sent to the IoT dashboard so that the machine operator can actually take action. There is a second data path that goes here on the bottom, where we're using CamelK as serverless integration component to copy all the data received via MQTT and store it in a Kafka topic. And that can be used for multiple different use cases. So you could think about multiple different additional applications, like, for example, predictive maintenance or others, to actually feed on that event stream in the factory. But we're also using Mirror Maker to actually mirror those Kafka event streams into the central data center, where that data is then stored in an S3 bucket based on OpenShift container storage to provide a data lake, for example, for model training and also the other use cases. And the trained model will then be sort of fed back into the factory data center. All of this is supported by our application development environment. So we have a cloud-based IDE, we have CI/CD pipelines that are running, and we will show you all of this stuff later on. Key important takeaway is we have our application is not just a single thing or it's something that runs in a single execution environment, but it's really multiple different components working together that need to be orchestrated across multiple different execution environments. And this is the interesting part where we sort of specifically designed our GitOps repository to sort of allow that for us. So let's take a look at that GitOps repository real quick. I have it over here. Our Manuela GitOps repository is really separated into three different directories. Key one are config and deployment, and we'll ignore meta for now. Config is really containing the application instance configurations. So if you look at config instances, you can see different applications. And for example, a single application, let's take the Manuela StormShift instance running on GCP, consists of these three different high-level components. We have the machine sensor, we have the line dashboard, and we have that messaging component that ties these together. We have a separate application, which is the Manuela data lake, which consists of the Mirror Maker, the S3 store, and the Kafka configuration. And as you can see, if we stick with the Manuela instance here, there is no indication of where actually what runs. So we have a single directory that allows us to really look at all the application components in the context of each other and see, for example, the configuration of the line dashboard here. And similar to what Ricky showed you, we're using the customization approach to sort of pull everything together into a single thing. Now, because basically we have multiple different instances of our demo application. We have one here for GCP. We have a second one for AWS, for example. We would, if we just had all the configuration items stored here in all these directories, we would have a lot of duplication. So we're actually using a templating mechanism. And if we, for example, look at the customization here, you can see that we're actually pointing to a base, which is then in templates directory and points to, for example, template Manuela OpenShift prod, which is the production configuration based on OpenShift for the application. And all of these configurations are stored here in templates, right? So we have layers of templates using the customization mechanism in order to ensure that no configurations actually duplicated anywhere. We have a very efficient way to actually store and depict just the differences in our individual instances. If we're now looking at how stuff is actually deployed over the different execution environments, we have here in our deployment directory the multiple different execution environments. So we have one for the line data server, we have a second directory for the factory data center, and we have a third directory for the central data center. And basically by sort of pointing with symlinks to the configuration of each component, right? We can ensure that a single component is, for example, deployed to the line data server, two components are deployed to the factory data center, and so on. So really, both views allow us to reason about the application. The configuration view allows us to reason about all the components of an application in their context. And the second view, the deployment view, allows us to reason about what is actually running where. You can see, for example, here, the factory data center, right, there's components running from the data lake, but also of our Manuela application. In practice, all of these configurations are applied by Argo CD, and this is already what Ricky already mentioned. This is what the provisioning of the environments is already preparing for us. So we have an Argo CD instance also provisioned that is then perform the application rollouts. So if I, for example, look into our factory environment, right, to our Argo CD, you can see that, for example, here in the factory data center configuration, I probably need to reload that. Just a second. Oh, that's a great one. Ricky, I might need a little bit of your help here. Seems like the cluster is misbehaving. Let's see if the other one's still there.
Let me check.
So I'll show the central data center then, which is sort of similar view, just different cluster while you're checking. In the central data center, you can see, for example, that we have these 3 different applications actually being rolled out. And if we drill down, for example, into which one is it here, our central Kafka instance, you can see all the stuff that is being deployed here, which really makes up the whole application. So all the different artifacts that make up the Kafka cluster and some additional stuff associated with it, right? So this is the standard stuff that Argo CD does. It basically takes whatever is defined in Git repository and applies it to the cluster. And if there's any change in the Git repository, it will pick it up and change the manifests which are running in the cluster. I haven't shown you the actual dashboard application yet. So I'm still in the working on the corporate hub because that's the cluster I know that's currently working. So let's quickly look at the IoT dashboard in the corporate hub, which is our testing instance. And here, let's just quickly reload that. Here you can see sort of the application actually running and gathering data. That is sort of the live data that the sensor simulators are actually sending out here. And that is being rendered as nice graphs as the data sort of pours in. And what you can see is we have 2 different simulated production machinery here. We have in the flow 1, line 1, the extruder 1, pump 1 down here, and we have the pump 2 up here. And pump 1 is sending just vibration data, and pump 2 is sending both vibration data as well as temperature data, right? So the vibration data on the right-hand side and the temperature on the left-hand side. This one down here just sends the vibration data. And the first thing I wanted to show you is how we're using GitOps approaches in our central data center to simply deploy a change to the edge, for example. To do that, I would be changing a configuration of our sensor simulator that runs near the production line to also send temperature data. So let me navigate over here, go away from the actual deployment thing into the configuration. Let's close this. The instance that is running on GCP, I look for the machine sensor 2. Sorry. Yes, I think that's the right one, where the sensor temperature enabled is set to false, and I simply set it to true. Now that change is now basically just on my local laptop. So that is now being flagged as a change in Git. And I can simply now commit that to Git by saying, giving it a comment. So let's say enable temp sensor 2. And I push that to our GitOps master. And that way, sort of the Git configuration now says that the temperature sensor should be enabled. And if we were to wait a couple of minutes, right, Argo CD would automatically detect that there's a delta between the Git configuration and the as-is configuration and apply that automatically. Now, I'm not a really patient person, so what I'll be doing is I'll just sort of tell tell Argo CD to sync, and that will sort of speed up the process a little bit so that it will ensure that the new configuration is applied when I tell it to, but usually we do it like every couple of minutes automatically. And what I would expect to be seeing is in like a couple of seconds that a new sensor data is appearing here because that configuration has been applied. By the way, while I was talking, you saw an alert flashing in. That was, for example, an anomaly that was being detected over here. So really what you can see here is an abnormal high amount of vibration that was being detected, and our anomaly detection model has already picked that up and sort of displayed an alert here. So let's see what Argo CD is doing. It says it has synced everything. That is great. See what's out of sync. Nothing right now, so I would expect that stuff. Oh, let me check if I actually did the change in the right. Of course I did it wrong, right? So what I did is I chose the wrong application instance. So I chose the one running here on GCP, whereas I would have had to do it because now I tried to change the configuration of the cluster, which was misbehaving. I can see if that cluster happens to be working now. So that is this one over here. Let's quickly reload that. Okay, that is behaving. And we're still waiting for Argo CD to pick up the change here. But let me quickly do the config change again for the right one, which is the Manuela test version down here. So let's go to the sensor, which is still disabled here. That's our test environment in the central data center. So let's enable that as well. Save it. Push the change to Git, enable temp sensor 2. And now we can tell Argo CD to pick up the change. Sync this again. And that usually takes a couple of seconds. And yeah, we can see the syncing process now starting. What usually happens, or what happens in our GitOps configuration, is that we have a job which usually runs in the beginning. Now we can see the machine sensor configuration being out of sync, so the deployment is adapted, and it basically starts rolling out a new configuration to the pod. So now that it is restarted, I would expect a new data to appear in our graph. Let's see once that comes up. It looks a bit funky here. Bam, now the temperature data is actually available without us having to actually go to the line dashboard, changing something in the configuration, etc. So I'm a bit conscious of time here. And we have only half an hour left, and I want to give Stefan ample amount of time to do stuff. So let me quickly shift gears here and go to the second thing what I wanted to show is basically how application development actually takes place. And quickly going back to the slides, let's quickly go to the documentation that is here. All the things that we're doing, all the demo steps that we're doing, they're actually documented here. So on the very bottom right, you see for each one of the steps that we're doing, how to actually prepare that in our blueprint, then how to actually run through the demo, so that if you want to do it yourself, you can do that as well. Same thing has happened for the code change thing that I wanted to show you. That is sort of the scenario where if we look at our demo application here in the detail, we can see that the temperature values are abnormally high. This is not something we expect. We would expect the temperature to be like in the below 100 Celsius range. And given our superior analytics skills and debugging skills, we have identified that this is due to an unnecessary, there it is, Celsius to Fahrenheit conversion here. So really somebody was trying to do too much, and they added a Celsius to Fahrenheit conversion, which is actually not required because we are depicting our degrees in Celsius. So this is actually too much, and I'm commenting that out. And sort of now I want to run through a coding change. So contrast to what I did before, where I changed the GitOps repository and that was applied through Argo CD, our coding change needs to be baked into a new container image, and then deployed to the production environment. And we're basically doing that by committing our code change to Git, fix Fahrenheit to Celsius conversion, and push it to the central GitHub repository from where our CI/CD pipelines can pick it up. Now, the CI/CD pipelines, they're basically configured in a project called Manuela CI. Let's quickly go there. You can see a number of pipelines and pipeline runs here having succeeded. Let me quickly kick off that pipeline run. If we were spending a lot of time configuring our environment, we could probably have done that also through a GitHub trigger. But let me just quickly instantiate a new instance of that pipeline, and then we can see what it looks like running through it. So here you can see down here a new instance of our build and test pipeline being instantiated that sort of adjusts this consumer component. And at this specific environment, right, it's just a linear sequence of tasks. First, we clone our dev environment. Second thing is we clone our operations Git repository. Then we increase sort of the build number, perform an S2I build, push sort of the information of which build number we're at back to the development repository so that we keep track of the build number that we are having. Then we're modifying our GitOps repository to sort of pick up the new container version, push that back to GitOps, ensure that Argo CD syncs everything, and then we would run to a number of smoke tests. And once these complete, right, we trigger a staging process that sort of this is also staged to a production environment where an end user or where somebody responsible for production can take a look at it and decide whether to actually put that into production or not. And then we do some cleanup tasks. Now this will run roughly about 5 to 10 minutes. So I would, given that we're running a little bit short of time, I would give it back to either Ricky or Stefan to see where we're at, and maybe we should run now through the data science parts of it and take a look at the changed code maybe later if we have some time.
Yeah, we can do this definitely. So quick question to Ricky: is the cluster deployed, or should I go on with the data science part, data machine learning part? Let me know.
The machine learning part, I would say, because you can do that in the hub, right?
Yeah, that's also. I will do this. Yeah, so no problem. Yeah, so that's great. So then I will. Let me move that Zoom thing out of the way and share my screen again. So I think that should work. So let me jump into. So just to double check, can you see my screen here? Should be some OpenShift installed operator thing. Okay, great. So. Yeah, Wolfram mentioned in this overview that we train a model and deploy a model, and what we're using here actually, we're using then a project that's called Open Data Hub, and the Open Data Hub is a kind of meta operator that can deploy a couple of tools and projects that's available for machine learning. I will just show you here a quick overview, like the components that are available in this operator. The main thing what we just used today is here is the Jupyter Hub for the workbench for the data scientist. There are many components also like Spark, Prometheus, Grafana, etc. But we will use Selden. Yeah, you might recognize that Wolfram was mentioning Selden. We're using Selden as tool for serving the machine learning model in the production environment, and Jupyter Hub for the model deployment. So in this setup, I deployed this operator already, and when you maybe I can switch to the namespace quickly, and it's nothing for the data scientist, but you will see that the Jupyter Hub is running here fine, and I can switch now over to my Jupyter Lab. So the first thing what I will do is actually I will tune the model. So I will go over the model on model training. I would clone the repository, and let me get this link from my cheat sheet here quickly. So I'm cloning now this repository with the code. That means all of the components are there. And the first thing what I will do here is going into the directory with the models, anomaly detections, and we have here 3 models that are all doing more or less the same thing. This last one here is actually the very first one with a lot of data exploration. We have a model that does the anomaly detection based on the TensorFlow model, and then we have a third notebook that is pretty simple and easy to demo, so simplified version. I can open that now, and you see here now also the intention what the data scientist tried to do here, detecting different kind of anomalies in the vibration data. So let me first clear all the outputs so that we can go step by step. So the overall flow is like read the data and preview the labeled data, doing some data wrangling, because from the time series data we need to get the data in a shape where we can do simple supervised learning, training a model, and then saving the model so that we can then save the model to Git and then build the container again. So let us walk through these steps here. Hopefully all modules are loaded. We will see that in a second if we're running into any errors. No, I think that's good. We have all Python included. So this is the data that we're reading in. It's time series data from the pumps, and it's the vibration data, and it's labeled data. That means at that point of time here, actually an anomaly occurred, and we want to now build a model that does this automatically. So if we look at the data briefly, so a couple of samples, we see here the vibration data and the top, and we see a couple of spikes here, and the second diagram shows the labels, and whenever this label is up here at 1, there's an anomaly, and for that we want to do actually the model. Yeah, so the data wrangling, we have some functions for the data wrangling that we are just loading here, and that's here in this small picture try to explain that what this is doing. So we have this time series data simplified like the seconds 4, 5, 6, 7, 8, and so on, the value and the label, and to train our simple model, we need to get this in this kind of shape where we have the features 1 to 5, and then the label, so that we can present that to the learning algorithm to easily get this model trained. So, and here we create now these episodes. We call this this row here, one episode. So we're converting the data here in this table format. This is now done, and we can also have a quick look at the data, like here, this table, and you see a couple of samples, the last 5 samples with those tail command, the features, and the last column is then the label. So next, like in every simple machine learning model, we need to do a couple of things: get the Y data, the X data, and that means the training, the features, and the and the result, the prediction. And what we're also doing, yeah, that's the format here now we have with the X data, the feature values. And we are also doing the splitting the training testing data. So because it's common practice, right? So you don't want to train your model with the whole data, because then you can't really find out if the machine learning model is biased. So therefore, with those train test split method from scikit-learn, it's pretty simple to split the data. So we have the test size of 33%. That means it's 2/3 of the data. We are training the data, and then we can validate that. So and now we see here we have a small data set, right? It's for a simple demo here. We have 1,000 samples and 2,000 samples with around 1,000 samples on testing data, and we have anomaly rate in the test training set with 2.7%, and in the test set 2.9%. And here the model training. So we have here a really basic decision tree classifier that we initialize and train and do the model fitting here, and then we try to see how the accuracy is. So and yeah, since that is simple data, we get a complete great accuracy of 100%. You see that's demo data. In real world, you most likely wouldn't get that high accuracy. And the next step, so to complete the flow, we can here now actually save the model to disk. So we saved it in this environment here in Jupyter Lab to disk. And we see then also an updated file here. This means we can also now say, okay, we have an updated notebook here, but we didn't change the notebook, right? So, but now we can say, let's we can now stage the data and also say, okay, like we have a new model trained, new model, so and commit it. Okay, I didn't set up my password here. I can simply, let me go over into my password store. 1 sec. So this should be my no, I think that's not the right one. Oops. No, okay. We don't need to commit it. So I put here some wrong email address in, but you get the flow, right? So in the Jupyter notebook, you can train the model, you can create a new model, save it, and then commit it to Git as the poor man's version of model versioning. So next we have that model now, and we also need to, we want to use Selden, and we need some Selden wrapper code. So that means that small piece of code that takes the model and presents to so that Selden can call it. We can try to find it here. Actually, we can also have a look here. Let's go back to the components. In the component tree, we have the IoT anomaly detection, and this code actually is the simple Python wrapper. So you see it's only a couple of lines of code. It implements the anomaly detection class, reads the model from disk, and then Selden would call the predict functions, and this predict would simply go ahead and call the classifier. What we also see here, some additional lines of code because we added some custom metrics, which is also pretty simple. We're returning the actual value and the prediction. So later on, data scientists could use then Grafana and to see, for example, if there's some model drift. So that means this piece of code we can now, or it's already saved, but when there's a new model, we can go exactly into the same pipeline that Wolfram showed. Let's go back to the project, actually, the manual CI, and we can go into pipeline runs, and let me just kick it off, and let me.
But you can see actually the stuff that we kicked off a couple of minutes ago now being completed. So our code change is already staged for production and rolled out to the manual test environment. And Stefan will pretty much start similar pipeline now for the machine learning parts.
Let's see if I'm in the right project. So and it's the same command, like, so let me get this from the history process. Yeah, I'm getting the template, and we're using the template for the builds, for the pipelines. But now here in the component is IoT anomaly detection, and with that I can kick off the build, and you would also see, hopefully then here now, this build started, and yeah, it picks up the code, the wrapper code. It gets Selden in place. It picks up the newly created model, which we now didn't push because of my fat fingers with Git. But you get the concepts, right? So we are building a model and then having a new container available that can be then first go into the test, and then later on into the production. So that's then the overall flow, how a data scientist gets the data and creates new models and uses these Tekton or OpenShift pipelines to push out the model on one hand into the testing staging, but then also via the GitOps approach into production. So with that, I just want to show you maybe one diagram because of the end-to-end flow. I think Wolfram explained already a lot of pieces here, but what we really saw is the flow where a data scientist is working here with Jupyter Hub, and then saving the model into Git, then the CI/CD pipeline, creating the model with creating the container. Creating the container with the new models. This gets into the image registries and then gets pushed out into the production. And these are the components like data flows from the sensors, from sensors to AMQ, the consumer calls, then the Selden core, and you saw also in the demo that sometimes an alert is popping up when anomaly is detected. And because of the lack of time, I think we would just go quickly again over the flow, like data comes into the data center. You see here the broker, Camel K integration. Maybe we can have a quick look at the Camel K integration. That should be eventually at the factory. Let's see if I can. This should be in StormShift messaging. I can see the Camel K, all instances, and because it's pretty simple. Here you see the MQTT to Kafka. Just an example. Jumping to the interesting code piece here. Here's the Java DSL implemented, and for example here this function then takes the data from the MQTT data from the broker, from that URL, and then push it into Kafka. So pretty simple. That's the power of Camel K here, and with the small DSL, it's all running fine. And then the whole flow is going on with Kafka Mirror Maker, and then from Kafka in the central data center, again through a camel route into the S3 bucket. So, and that's one example how we work that out with Camel K. Yeah, so that was the quick rush around that. What we could eventually look like, also how the machine, the build is still going on, but if you look now in our test environment, that should be.
Yeah, Stefan, so we have roughly 8 minutes left from our scheduled time.
Yeah.
So we could either use it to tie up some loose ends, or like, for example, shown that some tasks completed that we kicked off initially, or
maybe a great time to go back to Ricky if he wants to explain a few things.
Okay, I can just show once the cluster is deployed, how we do the self-registration process into ACM. Let me share my screen.
So we get context switching back to infrastructure provisioning that is completed by now.
Yeah, we render the blueprint to get some manifest that we passed on into OpenShift installer. And now once the cluster is deployed, what we are going to do is basically deploy clusterlet, which is the agent running on the managed clusters from ACM. And then all the configuration will be triggered, all the components will be pulled down, and in theory, it will reflect the state that we have in the Git repo, right? So since I explained before, we have 2 stages for day 2 operations. We have cluster add-ons, which are basically the clusterlet plus some operators that we need, and 03 services, which are the applications. We have in KNICTL tool, we have automated this into only 1 step, which is apply workloads. And then we can leave this running. It downloads the blueprint again in case there's any update. It renders the manifest, and it starts applying some manifests like cluster role, namespaces, secrets, service accounts, deployments. This is failing because the custom resource definition is not yet in the cluster. So when we apply or when we create an instance of that custom resource definition, it fails. But we have a loop that tries for some time. So if we go back to our ACM dashboard, we see that this is in pending import state, the stage in AWS. So this takes a few minutes, but in theory, the clusterlet will contact ACM. There will be with a specific token, and ACM will recognize this as a pre-provision cluster. So it will basically allow the registration into ACM. So once this registration happens, ACM will start applying all the components into the new cluster. So now we see that pending import is now in pending state. It takes just a little bit of time. Here. At the beginning, we will see only ready state. And it takes a little bit of time to deploy all the components that make like an introspection into the cluster. And at that time, once all these components are deployed, we will see the version of the cluster, which is basically the same as this one, where it is running, how many nodes. So we will see all this information. Okay, now it's in ready state. For example, one of the components that we are deploying into the edge is Argo CD to, to manage all the manual applications. So we should see here, this is the subscription, the subscriptions that are pending in ACM. So applied, we have to the local cluster, which is the hub. We have propagated the subscription to the staging GCP. And now we should see, where is the refresh? Let me refresh this. Well, not to lose too much time, maybe we can show the code change, the new sensor that Wolfram pushed before. In a couple of minutes, we should see here staging AWS as another cluster that has this subscription applied to. So if you see here, the local cluster, which is the hub, has the status propagated, but all the edge clusters will have subscribed state. So let's go back to Wolfram if you want to show that sensor change. Can you hear me?
So I've been talking on mute, so the typical Zoom thing that everyone does every once in a while. But I already ripped the screen sharing away from you. So here you can see that the pipeline run that I triggered has completed successfully. The one that Stefan triggered has now completed as well. What you can see here, this is still the staging environment where we do all our tests. And here, if we take a look at the dashboard, you can see that the new code is actually already running because you can see the temperatures are now in much more sensible ranges here. However, if we switch over to our production environment, right? So we're in the 50-ish degree range. If we go to our production environment, right? This is not yet the case. So production still runs the old code, which sort of has the Fahrenheit conversion in there, and we're running in some 100-something degrees here. And this is because we're still doing a manual approval step in our GitOps approach. So really, if we take a look at our GitOps repo, right, we have created a pull request between two different branches, and there sort of we have to approve manually that change has taken place. We can review the changes, can see what has actually changed. Now we are referencing a different version of our anomaly detection here. This is from Stefan's run. And we are referring to a different version of our IoT consumer application here. And with those changes, if I was to merge this change from our staging branch into our master branch by approving this pull request, I would then sort of move this whole thing, this whole change into production. And we would also see, if I did that after a couple of minutes, our production environment changing. And with that, I hope I tied up all the loose ends that I left open and would give it back to Stefan for some closing statements.
Yeah, good. Thank you. So let me share my screen again. Again, finding the right Zoom window. Okay, here we go. Share. No, we don't want to have that here. We are not in the Q&A. Yes, just to reflect what we've seen, and I won't go through all details here, but we've seen this core data center with Open Data Hub, with the whole concept of advanced cluster manager, configuring the clusters in the edge and the factory edge. On the factory edge, the whole concept of getting sensor data into the system, pushing the data via Kafka to the central data center, using Selden for model serving, etc. So that is, again, for wrap up the high-level conceptual build, where we say, okay, we get sensor data information from the factory back to the central data center into a data lake, and the code and configuration is pushed through one hand from the GitOps approach, another hand to bake in the code and also the machine learning models into containers. And the last slide, which I want to leave here, is actually 2 links or call for actions, a short LinkedIn post about the goals of solution blueprints from our colleague Nick. And this other URL is the Git repo where we were working the most time here, with all the explanation and how you can reproduce that and how you can try to find a way how you eventually could leverage that for your deployment. So, and you can also leave their comments in the Git and either with issues or contacting us. With that, I would like to say first of all, OpenShift TV, thank you for hosting us and giving us the possibility here to share the blueprints. Thank you to Ricky and Wolfram for the late evening show here, and hopefully see you soon again on OpenShift TV.
Yeah, thanks a lot, guys.
Thank you very much, guys.
Yep.